Hello friends, I welcome you in lecture number 26 on hypothesis testing. In this lecture we are going to discuss one question on the hypothesis test on the equality of variances. Sometimes it is also known as F ratio test for the equality of variances. We have discussed about F ratio test in lecture number 25 on hypothesis testing. So if you have not seen that lecture, I suggest you to watch that lecture first and then go for this lecture. And we recall that the test statistic for this type of F ratio test is nothing but capital F equal to S1 square over S2 square with the assumption that null hypothesis is correct. We assume that two population variances are equal, and under that assumption this ratio follows an F distribution with n1 minus 1 degrees of freedom in the numerator and n2 minus 1 degrees of freedom in the denominator, where n1 and n2 are the sample sizes. So to use this test, F ratio test, we require two assumptions, that the populations must be normal and the samples must be independent. And under these two assumptions we can apply this F ratio test. So all we have to decide is we have to find out what is the sample size for each sample, and we have to decide sample variances for each sample so that we can calculate the value of test statistic. And using F distribution table we will decide critical values for this distribution. So we understand first this question. This question was asked in GTU Winter 2019 exam. Two samples of size 9 and 8 give the sum of squares of deviations from their respective means equal 160 inches and inches square and 91 inches square respectively. Can they be regarded as drawn from two normal populations with the same variance or equal variance? So they have asked to answer this question, that whether we can regard these two samples from two normal populations whose variances are equal. So can we conclude from this data related to samples that population variances are also equal? That is the question which we have to answer here. Here we have two samples of sizes 9 and 8. So first we write down whatever is given in terms of our notations. Given that, suppose we consider first sample size as n1 and we consider n2 equal to sample size for second sample. And here sample variances are not given, but they have given the sum of squares of deviations from their respective means. So suppose the variable for first sample is say capital X, and variable for another sample is say capital Y, then X bar will be the notation for sample mean of first sample, Y bar will be the notation for sample mean of second sample. So first we write down what is given for first sample and then we will go for second sample. So for first sample we are using capital X, and the sample size we have written, it is n1 equal to 9, and we are given the sum of squares of deviations from their respective means. So if we have this type of observations in the first sample, say x1, x2, x, n1, then suppose x bar is the sample mean, then we are given the square of deviations. If we take x1 minus x bar, then this is called deviation of x1 from mean x bar, and we have to take square. So this is the square of deviation for observation x1. Similarly, if we consider x2 minus x bar square, then this is for second observation, and so on. So we have to consider this sum of squares of deviations for each observation. So this we can simply denote by sigma capital Xi minus x bar whole square. So we are given this value sigma Xi minus x bar whole square, or we can ignore this suffix also. We can simply write that sigma x minus x bar whole square. So that is given for both the samples, and first we write for first sample. Similarly we will write for second sample. So the sum of squares of deviations from their respective means equal 160 inches and 91 inches. So we consider this for first sample and 91 for second sample. So it is given that sum of squares of deviations from mean x bar is 160. But we require sample variance, and suppose sample variance for first sample is denoted by S1 square, then using the formula of sample variance we can write that it is sigma x minus x bar whole square divided by sample size minus 1. So we have 160 and n1 minus 1, that is 8. So this is 20. So we are not given sample variance, but we are given this sum of squares of deviations. So using the formula for sample variance we can easily find out this S1 square, and it turns out to be 20. So this is for first sample. Now same procedure we repeat for second sample. Suppose we consider sample 2. Sample size is given as 8, and here we are using variable y. So we have y minus y bar square, that is sum of squares of deviations from mean is 91 for second sample. So now we can calculate sample variance for second sample denoted by capital S2 square. Using the formula of sample variance we have 91 divided by n2 is 8 minus 1, 7. So this turns out to be 13. So now we have all the required values for applying F ratio test. We require sample sizes and sample variances to calculate the value of test statistic. Now we start with our formal procedure for hypothesis testing. First we state the null and alternative hypothesis. We are asked to check whether the samples can be regarded as drawn from two normal populations with the same variance. So suppose we assume that samples can be regarded as drawn from the two normal populations with equal variance. So we assume that this is correct, and negative statement for this is that population variances are not equal. So sigma 1 square and sigma 2 square are not equal. So this is the example of two-tailed test, and this we will assume that this is correct. We always assume that null hypothesis is correct, and we test that null hypothesis whether we have to reject it or we fail to reject it. Level of significance is not given, so we assume that level of significance, we consider that level of significance is say 0.05 or 5% level of significance. Now it is given that both the populations are normal. We require those two conditions also to apply F ratio test. So it is given that both populations are normal, and whether they have given independent conditions or not. Given that both populations are normal and they have nothing specified about the independency, so we have to assume that samples or populations are independent. So it is not given. So that we have to assume. To apply F ratio test, we must check these two conditions. So assume that two samples are independent. So if these two conditions are satisfied, then only we can apply F ratio test. So whatever condition is not given in the question, we must assume that condition, otherwise we are not able to apply F ratio test. So now under this assumption, and because null hypothesis is correct, we can say that test statistic for this hypothesis test is F equal to S1 square divided by S2 square, and numerator degrees of freedom will be N1 minus 1, denominator degrees of freedom will be N2 minus 1. We have obtained both the values, S1 square and S2 square. S1 square is 20, S2 square is 13. So this value is 1.5385. This is the calculated value of test statistic. Now next step is, as usual, we have to decide critical regions, and for that first we have to check whether our test is two-tailed test or one-tailed test. Here we have two-tailed test because there are two possibilities: sigma 1 square is less than sigma 2 square, or sigma 2 square is less than sigma 1 square. So this is a two-tailed test, therefore we will divide our level of significance by 2 and we will consider equal area in both the tails. And we are familiar with the shape of F distribution. It is having a skewness on the right side and the graph is not symmetric, it is always asymmetric, and for higher degrees of freedom it can be symmetric, but here degrees of freedom are 8 and 7. So here we have 0, it is always non-negative, and we roughly try to sketch the graph of F distribution. So it is having a longer tail on the right side. Values of F are on horizontal axis, and because we have two-tailed test, we have to divide the level of significance into two equal areas. Suppose these two areas are equal and they are equal to alpha by 2. Alpha by 2 is nothing but 0.05 divided by 2, that is 0.025. So this point will be denoted by capital F suffix 0.025 because area to the right of this point is 0.025. This area is also 0.025, and this notation F alpha says that area to the right side of that point is alpha. So for this point we have to find out this alpha. So for that we require the area to the right side of this point. Area to the left side of this point is 0.025, and we know that area under the probability density curve is always 1. Therefore area to the right side of this point is 1 minus area to the left side of this point, and that turns out to be 0.975. So here I denote this by F.975, and these two are rejection regions. These 2 points are critical values of F distribution, and area to the right of this point is rejection region. Here this point, area to the left of this point is rejection region, and in between we have non-rejection region. So now we should decide values of these two critical points using F distribution table. Now F distribution table always gives us critical values f alpha such that area to the right of f alpha is alpha. So now I am going for f distribution, and here area to the right is 0.025. So I have to search for f distribution for alpha equal to 0.025, and the numerator degrees of freedom are first sample size minus 1. Here first sample size is 9 and size of second sample is 8. So numerator degrees of freedom is 9 minus 1 equal to 8. Denominator degrees of freedom is 8 minus 1 equal to 7. So I have to use f distribution table for alpha equal to 0.025 with 8 and 7 degrees of freedom. That means from f table I have to decide f 0.025 with nu1 equal to 8 and nu2 equal to 7. So now I am going for this table. These are the critical values of f distribution for alpha equal to 0.025. That is, area to the right side of this point is 0.025, and nu1 is 8 and nu2 is 7. So I have to search for in column headings for 7. So here I have to go up to 8 here. These column headings are values of nu1, and this left column corresponds to values of nu2. nu1 is 8, so I have to go up to this, and nu2 is 7, so I will look in this row. So I am taking intersection of these two rows, or this row and this column, and the point of intersection is our required critical value. So now let me remove this, and we have this f suffix 0.025 with these degrees of freedom is 4.8993, or if we round off up to 2 decimal places, we can say that it is 4.90. So we will consider 4.90. This point is 4.90. Here also I can write this is 4.90. Now what about this point f.975? So for finding this critical value, we recall this identity which we have seen in the lecture on f distribution. Critical value corresponding to 1 minus alpha with nu1 degrees of freedom in the numerator and nu2 degrees of freedom in the denominator is 1 divided by f alpha with nu2 degrees of freedom in the numerator and nu1 degrees of freedom in the denominator. We have to interchange degrees of freedom, and if I have 1 minus alpha here, I will consider f alpha here. Using this result, we decide that critical point, which is f.975. So here nu1 is 8 and nu2 is 7. This f suffix 0.975 is nothing but 1 minus 0.025 with 8 and 7 degrees of freedom. So you can see here alpha is 0.025. So here I write f suffix 0.025, and I have to interchange these two integers. So here first I write 7 and then 8, and I have to look for nu1 equal to 7 and nu2 equal to 8 degrees of freedom in the f table. So let me remove this now. Now our degrees of freedom are different. We are interchanging these two. Here I have 7 and 8, and alpha is 0.025. So now I have to go below this column, and here nu2 is 8. So I will take intersecting point of these two lines, and that is nothing but this point. I have to take intersecting point of line corresponding to nu2 equal to 8 this is line corresponding to nu1 equal to 7, and the intersecting point is this point. So now I remove these two and I find that my critical value is 4.5286, and if I write up to 2 decimal places it is 4.53. So here I have 1 divided by 4.53. Now let me take this division using scientific calculator. This I find as 0.22. So this critical point is 0.22, and be careful, we have to use this result f1 minus alpha nu1 nu2. Here alpha is 0.025. We have interchanged these two, and using f table this value is 4.53, and 1 divided by 4.53 is 0.22. So we have now these two critical points. This is 0.22 and this is 4.90, and I have to compare with calculated value of test statistic. If we round up this, then it is 1.54. So where is 1.54? Whether it is less than this or greater than this. So this is 0.22, this is 4.90. So we can say that this value, it is always in between these two. 1.54 is less than 4.90 and it is greater than 0.22. So we are in non-rejection region. So that means we fail to reject the null hypothesis. So now I have to write that this value f.975, this we have obtained as 0.22, and what is calculated value of test statistic? It is 1.54. So it is f equal to 1.54, and this is less than f 0.025, which we have obtained as 4.90. Okay, so this means we fail to reject the null hypothesis. So null hypothesis is that population variances are same, and our question was that can we regard two samples as drawn from the two normal populations with the same variance. So we can say that samples can be regarded as drawn from two normal populations with the same variance. So in this way we can apply F ratio test to check the equality of two variances. So this is all about this session. In the upcoming lecture we will discuss some more problems on the F ratio test. Thanks for watching.